All right, so we've got our quiz. We've got our quiz tomorrow, and I'm gonna second block is actually not gonna take theirs till Wednesday because they were tired of you guys always getting better grades because you would always ask them after the quiz what was on it, and they would tell you, and that's why you guys did all a lot better. Is what they said. I don't know. That's what they said. So. Actually, that's not the reason. The reason is there's something going on tomorrow during the second block, and so that's going to throw off the quiz procedure for them. So, they're on a little different schedule for the first part of this week. But for you guys, it'll be just business as usual, and so the quiz will be tomorrow. So we're going to spend our time kind of reviewing and going through that, and giving you some practice kind of things to do. I don't really have an assignment as far as some review problems, though, to do, like for homework. So that's going to be more about you just working on your own and going back through and reviewing notes and studying that way, which is not, in math, it's nice to have some problems, I understand that. So we'll try to do some in class and try to make sure we go through all the different examples, and then you can use that as a guide to make sure you go back and review that. So if we start here with our kind of the notes that we had been talking about earlier in the week, or early last week. So the things that we have covered, what I'd like to do today, the plan is kind of go through kind of the highlights of what we've talked about, try to, I've kind of got an analogy to algebra that I've tried to want to talk to you about to kind of keep some of this straight, what you have to do, because there's a lot of different things. And then go through the homework, see what questions you have there, and then throw up some other examples that might not have been in the homework here of things that will be on the quiz. And hopefully that's pretty full, review of the things you have to know. So we started off, so trying to get a little bit of a big picture idea here of this stuff. We started off with the definition of the derivative, and that is just key understanding that you know that when we use that language, the definition of the derivative. Now, sometimes we call it the limit definition of the derivative. Sometimes it's called the formal definition of the derivative, but that's this thing right here, okay? The formal definition of the derivative, the limit definition of the derivative, the so-called long way. But understand that you will not go through that process using the limit definition of the derivative, the definition of the derivative, unless the directions specifically mention it. If the directions don't specifically mention the definition of the derivative, then you won't be going through that process. Okay? And then we use that to come up with this shortcut power rule, which is pretty cool. So if you need to do a derivative in a problem and it doesn't mention the definition of the derivative, then we can use shortcuts and so forth, like on 52 and 54, today's homework. Max, min, chart kind of plots, which we'll get to here in a second. Okay? And then we took this kind of side trip into limits, and this is where the confusion starts to come in. I know this is something that in the past some people have struggled with, and a lot of times I don't find it out till later, but once we create the quizzes and stuff like that, but there seems to be some confusion about limits and derivatives, and what's the difference, and when do you do a limit, and when do you do a derivative, and what's that mean, and all that stuff. And so I really want to focus on that today. The overriding calculus thing we're doing is derivative. What is a derivative? Slope at one point, or rate of change. Those two are interchangeable ideas. Instantaneous rate of change, slope at one point. Derivative is the slope of a curve at one point, the instantaneous rate of change of a function at one point. That's what derivative is. The question is, how do we find derivative? How do we find the slope at one point? How do we find the instantaneous rate of change? Well, we're going to talk about that today. There are several ways we can do it. One of the ways is this definition. Right? And so it has a limit in it. So in working that out, we have to be able to do limits. So we spent some time talking about limits. A lot of time talking about limits. And we worked on all the different things that we might have to do. Factor and cancel, common denominator, get a conjugate, maybe do a table on our calculator, maybe just look at a graph. These are the different things that can happen. You can get a number, it could be does not exist. All that stuff happens with limits. So in the process of us doing these limit problems, we then kind of got lost in what's a derivative and what's that mean. Okay, so it's very important that we understand that difference in that idea. This worksheet was even called limits and derivatives, right? So here's where we see the intersection. Here's where we see how this kind of comes together. This idea of limits and derivatives on that worksheet. Okay, and then after we were done kind of with that side trip and doing these limits, then we came back to the idea of derivatives. And we said, okay, now here's what we want to do in calculus. We want to do problems with derivatives that help us find some information about functions, which is what the chart's all about. When is a function increasing, decreasing? When does it have a local max? When does it have a local min? Where's its inflection points? All that stuff. And how can we use these new shortcuts and all that stuff to be able to do that? And that's what problem 52 was about. Problem 54 was about. All right. Then the last new thing we did, which was on Friday, was this thing, this definition of a continuous function. What does it mean for a function to be continuous? Well, a function's continuous, so this really goes more with the limit stuff. This doesn't have anything to do with derivatives. What's it mean for a function to be continuous? Well, it basically means you don't have to lift your pencil. There's no holes or breaks or gaps, jumps. You don't have to lift your pencil. Well, what are the three things you need for a function to be continuous? Well, you need these three things right here. There has to be an output at that point. These two situations would fail that. There's no output at those points. So it's not continuous. You'd have to lift your pencil. Number two, the limit must exist. This break in the graph would fail. So that's not continuous. The vertical asymptote, again, the limit does not exist. The cars don't meet. And then this situation illustrates the third thing that has to happen is if the limit exists, if the first two happen, if the function is defined, if there is an output, and the limit does exist, they have to be the same. Because here's a situation where there is an output, and the limit does exist, but they're not the same. So you'd have to lift your pencil. So these would all be situations where the function's discontinuous, and these are the reasons. And you have to, on the quiz, be able to list those as your reasons. You're going to need to be able to identify what's causing those to be discontinuous. And we'll do an example of that here in a minute. All right. And then the last thing I would say, and I forgot, I didn't give you this on Friday, and I should have. And so you might want to jot this down. We've talked about it kind of informally, but I've never formally said, here, you've got to know this. A differentiable function, right? The term differentiate, that's another way to say do the derivative. If we say to differentiate the function, we're saying do the derivative. So a differentiable function means you're able to differentiate it. Means you're able to do the derivative. So the derivative exists everywhere. So a differentiable function is a function that is continuous and the derivative, f prime, exists everywhere. F prime of x exists everywhere. So here's two examples of functions that would be continuous but not be differentiable. This is kind of a square and a rectangle kind of thing. Some rectangles are squares, but all squares are rectangles. Some functions are continuous but not differentiable. Here's two right here. You never have to lift your pencil on these two functions, but the derivative doesn't exist everywhere. You got a sharp point, you got a vertical tangent. All differentiable functions are also continuous. And where do we see this? We see this in problems where they give you directions. They say, let f be a differentiable function. Well, that just tells you that there's not going to be breaks or gaps. It's going to be continuous, and there won't even be any sharp points or anything. Okay, smooth is often a word we use with differentiable. Because not only do you never lift your pencil, but you don't have any sharp points either. Now, it's a little bit misleading because this graph would look smooth, I would think, but it's got a vertical tangent line. So the derivative doesn't exist. So even that is not. That's a problem with informal definitions. They're not always technically accurate. Okay? All right. So with that, that's all. I mean, that's the stuff we need to know. I mean, that's a little bit of everything. All right. So now let's talk about what we need to do. So let's talk about this idea of limit versus derivative. And here's my example. I don't think you need to write this down. I think you just want to pay attention to this. This is my analogy for the difference between limit and derivative and what's going on. If I give you this problem, f of x, and we're not going to work it through, but we'll work through something similar here in a little bit. F of x equals cosine x, and I want to find f prime of 4. Right? Now, what are some of the ways we've talked about finding f prime of 4? Do what? I don't think it's sine. It's close. You're close. We didn't talk about cosine, did we, as a derivative? We talked about sine. The derivative of sine is cosine, but it doesn't quite work that way the other way. Plug 4 into what? No, because f, this is f. Say that again. See this, I'm glad we're talking about this because I still think we're not quite clear. Use a table on what? Graph cosine. Oh, graph cosine and pick 2 points really close. What do you mean make a table? I don't think so.
Oh, I know you have to make a table on every bar.
So like, you guys are thinking about like your worksheet here today, right?
Yeah.
On the worksheet where we set up an f prime, we did a table. See that, and I'm glad we're talking about this because a table, when we do a table, that's a limit thing, right? That was what we do when we're doing limit problems, right? This is a derivative problem. What's that? What we want is the tangent line on the cosine graph at 4, right? What Ryan said earlier, that what is a derivative? It's the slope of the tangent line. So what we want is the slope of the tangent line of the cosine. So one way would be, now it depends if this is calculator or no calculator, so we want to talk about this. One way would be to go to the cosine graph, go to 4, pick 2 points really close together. But you know what? That was chapter 1. We haven't been doing that lately, right? Can you think the last time you had to pick 2 really close points and do a slope calculation? That was back on our last quiz. We haven't been doing that now, right? So it's probably not something we're going to see on the quiz. Okay, what's another thing I could do? The definition of the derivative, right? Now, another way would be a shortcut, and that's what Allie tried to do, but we don't have a shortcut yet for cosine. But if we did, she was correct. If we did have a shortcut for cosine, well, as a matter of fact, you know what? I picked a bad example. I picked a bad example. I should have been on the same page Allie was on. Okay, let's go to that. Okay, so if f of x equals x squared, and I want to do f prime of 4. One way is to write f prime of x. You're going to hear me say that a lot this year, as a matter of fact. If you want to find f prime of 4, first find f prime of x. If you can find f prime of x, which when I say that I'm talking about with shortcuts, then plug a 4 in, f prime of 4 would equal 8. Does that have anything to do with the limit? No. It doesn't have anything to do with the limit or anything else. We would use our shortcut and we would do this. Okay, now, just a second ago, though, somebody said, what's another way we could do it? Allie, you said it. What's another way we could do it? The definition of the derivative. How are you going to know? It's going to be in the directions. So maybe the directions here said find f prime of 4 with the definition of the derivative. So then what would you write down? You would write down the definition of the derivative, which is limit as, no, h approaches 0. Yeah, it would be. Okay, this is a Monday, isn't it? All right, but we've got to get over that real quick because we got a quiz tomorrow. Okay, It's that, right? That's the definition of the derivative. So we've got to know the definition of derivative. So this is a derivative problem. The directions say use the definition of the derivative, which automatically takes us to thinking of this right here, right? The definition of the derivative. So we write this out. Now what? Now we plug this in. 4 plus h squared all over h. Okay, now, hang on a second. We now have to solve this limit problem. So now what has happened is we have now come from this being a derivative problem. Now we've gotten down to a step where it's now a limit problem. Okay, so what I'm trying to do here is distinguish for you between what's a derivative problem, what's a limit problem, when do those kind of come together and are in the same kind of problem, and when are they just separate things, okay? And that's important for us to understand. So, now we've got it down to a limit problem. Well, we have a few different ways we can do a limit problem. Factor, cancel, common denominator, conjugate, do a calculator table, whatever. Now on this one, I'll bet this would be in a no calculator question problem. Right? Because this would be a factor and cancel kind of thing. So we'd work it all out, and we better come up with 8, I'm sure. Okay? Now, if this would have been on a calculator section, and then that's what I was thinking in the beginning. Let's pretend for a second that this would have been cosine x instead. Now when we got down to here, we'd have had cosine 4 plus h minus cosine 4. We'd have done everything the same, but we'd have gotten to here, and now can we do algebra? No. So now we would do the calculator table, like what your worksheet was today. And you would take this yellow part, or green, or whatever color that is, you would take that part and graph it and look at the table. See what's happening here? Okay? So that's how you work out this limit problem. Now, distinguish that between just a limit problem like this. Let's say you had, does that have anything to do with the derivative? That's just a plain old limit problem. So how would I do that one? I would first plug 3 in. I get 1/3 minus 1/3, which is 0. 3 minus 3 is 0. 0 divided by 0. So I would keep going. So what would I do next? Bow tie. This is a algebra 1. There'd be a common denominator. We're going to do an example of this a little later. And we would do some algebra, and we would find the limit that way. It's just a plain old limit problem. It doesn't have anything to do with derivative. So on this side, okay, so here's my analogy. Here's how I want to try to compare this for maybe something you've seen in the past. Okay? So I definitely would not write this down. But in my Algebra 1B class right now, here in the future, we are going to be working on this problem right here. Solve this equation. And you guys are getting into this right now with our derivatives, right? We're doing derivatives, set them equals 0, right? So what would you do to solve this problem? You would set it equal to 0. So we'd bring the 6 over. And then what? We would factor, right? And we would get this. And then we would get x equals 6 or -1, and we would be done. Now, what I would do is I would point out to my algebra class, I'd say, okay, this is what we want to do. We want to solve this equation. In the process of solving this equation, we have to be able to factor a trinomial. So you know what? Maybe we should take a day or two and practice factoring trinomials. And so we're just going to factor. Now, is a factor problem the same as a solve problem? No, but can a solve problem have factoring in it? Absolutely. So we would come up and we would practice for a few days. We would practice some factoring problems just because at somewhere in time in a solve problem, we might need to factor. That is the best I could come up with, I'm sorry, as an analogy of what's happening here. This is what we really want to be able to do is derivative type problems. And sometimes in a derivative problem, if we're using the definition of the derivative, we set up a limit. And to solve that limit, or to be able to finish this derivative problem, we've got to be able to solve this limit. So we spent a few days doing limits. But they didn't have anything necessarily to do with these kind, but we just practiced solving limits. But sometimes in a derivative problem, a limit will be there. Okay? That's kind of the difference, I guess you might say, between derivatives and limits, and when they may come together and when you may use those things. All right, so maybe that helps a little bit. Maybe it just confused you more. I don't know. Hopefully it helped a little bit. Now, let's take a look at, I've got my notes that I made last night on my Tilly sprinkler landscaping bill. Okay, so the next thing I wanted to look at was number 66 and 67. Would those be good ones to look at? Okay, because these are so we're kind of working backwards, I guess, from newest to oldest. But the latest thing we've learned about is this idea of continuous function, and those three things we need for a function to be continuous. Okay, and that was back on this sheet. That was kind of this stuff right here. So here's the things we need for a function to be continuous right here. All right, so on 66, we were given this function ax plus 1 and x squared, and this is if x is less than 2 and if x is greater than or equal to 2. Now, the question on 66 said, find a, I think is right. So the limit as x approaches 2 exists. Is that what it said? So we want the limit as x approaches 2 to exist. Now, why in the world would the limit not exist as x approaches 2? Piecewise, so there might be what there? There might be a break. So when this line, we can tell that's going to be a line. When that line leaves off, maybe the parabola takes off up here. Okay? And there might be a break. So how do we tell if there's a break? Plug 2 into both, see what their y values are, because we want their y values to be what? The same. We want their y values to be the same. Then that means there would be no break. So if we put a 2 in here, we get 2a plus 1, and put a 2 in here, we get 4, and so we solve that, and we get a equals 3 halves. So what that tells us is if a is equal to 3 halves, then there will not be a break. This parabola will take off from the same spot the line left off. Now that is a problem you're going to have to do multiple different times, probably as we go through the year. Let me show you. This is a practice test. Let me scan through this real quick, see if I can find one. There's almost always one on here. This will be the one that won't, I suppose. I'll be able to see it pretty easily if it is. And sure enough, this one is not. This practice test is a lot of pages. Okay, that is not going to be good enough. That's close. Okay, I should have. I'm so confident. Okay, well, anyway. But you see here was a piecewise function on this one problem, but it just asked something different. It got into point of inflections. It was a little bit beyond what we're talking about right now on this problem right here. But this is really taking. I know, it's hard to. It disappears. Thank you. Where would I be? All right. So now, so anyway, so that's 66 part A. Part B says what? Does f prime of 2 exist. Okay? Now, how do we tell if f prime of 2 exists? Well, there's only two ways we know where a derivative doesn't exist, and that's what? When does a derivative not exist? Vertical asymptote. Well, okay, break. But we already know there's not a break, right? Because we just figured out if a is 3/2, right? There's not a break. The sharp point. Now we're not talking about limit doesn't exist. Now see, those are two different things, guys. Limit doesn't exist when there's a break or there's a jump or various things like that. Sharp point, when the derivative exists, means a slope. So sharp point. That's what we're asking. Now, think about this. When you have a piecewise function, if this line goes like this, and then let's say the parabola took off from there, well, that's a sharp point. Or let's say that it was going up, and then the parabola was on its way down, and then went up like that. That's a sharp point. What's the only way you could take off from a line to a parabola and not have there be a sharp point? If the slopes are the same on the line coming in as they are on the parabola going out. So, think about what we've just said. For the limit to exist, they have to have the same y value. For the derivative to exist, they have to have the same slope or derivative. So, let's put our 3/2 in here for the a. What is the derivative of 3/2 x plus 1? 3/2. What's the derivative of x squared? But we're talking about when x is 2. So what would that be? 4. So do they have the same derivative? No, they do not have the same derivative. The line has a slope of 3/2. The parabola, when it takes off, has a slope of 4. So what's that meaning? It's coming in like this, and then it instantly changes to be steeper. That's going to cause a sharp point. Anytime you have a sudden change in slope, that's what makes a sharp point. To not have a sharp point, you can't have a sudden change in slope. So, that's how you do that part B. Now, 67, here's what I love about how the book does these two problems. Because 67 is exactly the same problem, but it asks parts A and B in two completely different ways. But if you think about it, it is the same. Tell me the functions. Help me out. I'm not on that page. What's the ax squared plus 3, x is less than 2, 3x minus 5 if x is greater than or equal to 2. So again, we have something weird happening at 2. Now, what did they ask in part A? Instead of asking, does a limit exist, they said, just find A, right? But look what the directions were. It said f is what? Continuous. If f is continuous, can there be a break? There can't be a break. So if f is continuous, all they have to do is say find A, because we know there can't be a break. So that means when we plug a 2 into here, that'd be 2 squared is 4, this would be 4a plus 3, has got to equal what we get when we plug a 2 in for here, which is 1. Right? So it's the same exact problem as before. The last problem we said, find A so that the limit exists, which means there's not a break. Here they said, find A so that the function's continuous, which again means there can't be a break. Same thing, different question. So we take away the 3, we divide by 4, we get negative 1/2. So we know that the A is negative 1/2 on this function. Okay? What did part B say? Is f differentiable? What's that mean? Right? But more technically than that. Is f prime, does f prime exist? Right? Which is exactly the same question they asked in part B on 66. Is the function differentiable? Means it has to be smooth, there can't be a sharp point. So in other words, we have to do the derivative of each one of them again. So we do the derivative of this, that'd be negative 1x, and the derivative of this, 3, and again we're talking about when x is 2, so this would be negative 2. So is it differentiable? No. So the parabola is coming in, going down at a slope of 2, and the line takes off up at a slope of 3, there's going to be a sharp point, and so it's continuous, but it's not differential. Okay? So this is a really common type of question when you want to talk about continuous and differentiable functions, is they give you piecewise and they talk about this. So think about what we did. Every time you do this, where does it break? You plug that number in for x. You want the y values to be the same if it's going to be continuous, so there's no break. You want their derivatives to be the same if it's going to be differentiable. So it would be smooth slope transition. Yes?
So justify your answer with the different.
Yeah, I would just show your work, to be honest. I would just do f prime, like right here, I would say, okay, this is f prime, this is f prime, like, you know. Yeah, I think just your work. And then say, yeah, they're different, so therefore it's not different. Yeah. Okay? All right. I do want to go back to that practice exam, and I wanted to show you this. This is something that we'll be working on later, like in January, when we get close to our midterm and getting ready for our AP tests and stuff, because we're now starting to learn enough that we can start to see some of these questions pop up. Now, they're early. Look at this one. It's the very first problem. So sure enough, the very first problem right out of the gate, and this wouldn't be unlike probably your AP test, is a limit problem. This is a no calculator. You can barely see it up here. Calculators may not be used on this part. What are you going to do right here? I'm sorry, I heard several things. Conjugate. Conjugate. This is one of those 3 different types we've learned where you would do. So we would multiply the top by this. Now I'm going to give you a chance to practice one of these here where I give you some time to work and then we check it. But we would multiply here. Right? And so on the bottom, when we FOIL, we're going to get x minus b. Up here, we got b minus x times this. We would not factor that. Right? Do those cancel? Almost. Take out a -1. Right? Then they would. And now we can plug in our b. Now, I kind of skipped that step. We should have done that first. We should have plugged the b in first, substitution. B minus b is 0. Square root of b minus square root of b is 0. 0 divided by 0 means keep going. We're going to do a conjugate thing. Once those cancel out, now we can plug into b. Okay? So this isn't here anymore. So now we plug in our b. Square root of b plus square root of b is 2 square root of b. And then there's a negative on it. So choice A. Right? This is patterned right after the AP exam. All right? Matter of fact, I pulled up. I don't have it up right now. I pulled one up on the 2012, the actual AP exam from 2012. Problem number 2 on that test was a limit problem, just like this one. Okay? I want to go to the third one. This looks familiar, right? It should look real familiar here. Okay, look what this says. The graph of a function f is given. Which of the following is true? The limit as x approaches 3 is 1. No, the limit would be 3. It's where the cars meet, right? The cars meet up here at 3. Not true. As x approaches 4, the limit is 3. What's the limit? Doesn't exist. The one on the right's at 3. The one on the left is at 1.5 or something. The cars don't meet. Limit doesn't exist. F is continuous at 3. No. Now, here's what I want to review for the quiz. So I may give you a function like this and ask you, where is the function discontinuous? Or like this, is the function continuous at 3? And then I may say, if it's not, tell me why. And you have to give one of those 3 reasons in the definition. The limit at 3 does not equal f of 3. That'd be a great way to say it. The limit as x approaches 3 does not equal f of 3. That's the third of those 3. Because the limit is up here, and the output is down here. And that's what you would say. So that one is no good. F is continuous at 5. It's a sharp point, but does that matter for continuous? Continuous means you don't lift your pencil. Right? This is continuous at 5. So the answer is yes. There is an output. There is a limit. They are the same. The cars would meet. The cars meet where the output is. It fits all 3 of those. So yes, it is continuous. And then this one, the limit as x approaches 6 equals f of 6. Now you could get that one by process of elimination, right? Those of you that said D, eliminated D, once you get to E, you're going to go, wait a minute, now I eliminated all of them. And so you may come back to this one. Okay, so it is D. All right, one more. This one doesn't really have as much to do with the quiz, although it does. I'm not going to make you do this on the quiz, but it's something I want you to kind of think about, and it does connect with what we're talking about. They give you this function f, and then they ask for f prime of 2. Now, let's pretend for a second that you don't even know what this function is. Okay? They want to know f prime of 2. So we talked about this a minute ago. If you're going to find f prime of 2, what are some ways you can find f prime of 2? Definition of the derivative. But I would never do it unless they say use the definition. So I would not do the definition here. What's another way? Some shortcut, right? Like power rule kind of thing. Well, it turns out that doesn't work with absolute value. Power rule doesn't work with absolute value. But if this would have been like an x cubed or something, yes, that would have been the way to go. Do a power rule, plug in a 2. Okay, what's another way? Some sort of a graph. And estimate and that kind of thing, like a tangent line kind of thing. And that would be what you'd want to do on this one. Because this, and this would be a no calculator, but this is just a V graph, absolute value, right 2, up 3. So you take the V graph, move it to the right 2, up 3, and now what's the slope at 2? Does not exist. Because it's a sharp point. That's how you would do that one. But you see how you would run through those different options of how you could find f prime of 2. And what would fit for a certain problem. And this is the only one that would really fit here. I would never use the definition if you didn't have to. All right. And then finally, well, not finally, that's good enough for that. All right. Now, check my notes. It is. The bill is, I'm sure it's paid. All right. So, all right, let's let you practice a little bit. Since that's what we're just talking about, we're talking about definition and stuff like that. Let's look back at our at our notes here. And so we're talking about derivatives and stuff like that. So, and limits, how that relates to limits. So let's just do a quick couple of examples. So let's say I give you the problem f of x equals 2x squared minus x plus 1. Find f prime of 3 by the definition of derivative. And this is no calculator. No calculator. Okay, I'm going to show the answer up here. Don't look if you don't want to, if you're not finished yet. All right, questions about that? The definition is the f of 3 plus h minus f of 3. So we put all that there is where we plug our 3 plus h in for x. And then we plug our 3 in for x. We just get 16. That's that part over there. And I think I did all the algebra right. Things worked out nice. 18 minus 3 is 15. Plus 1 is 16. Take away 16, so that all cancels out. And of course, we also know by the shortcut, since we've learned the shortcut, we can simply do the derivative just to check, right? The derivative would be 4x minus 1. You put a 3 into there, you get 11. So the answer better come out 11. But on the quiz, you're going to get all your points for your work here, right? Not for the 11. Right? So if you just put 11 for this answer and use the shortcut, that's not going to get you anywhere. Okay? All right, now let's do this. So f of x equals tangent x. Now the directions are find f prime of 2 by the definition of the derivative, same directions, except the difference now is this would be on the calculator part, and I would say give, or I might say justify your answer using a calculator table. Okay, so kind of like when I was making that analogy to factoring, this is kind of what we're talking about, but this time I want you to actually do it. So get your calculators out and be ready to go there. Okay, I'm going to put it up here. All right. F prime of 2 by the definition of the derivative. Again, there's the definition. So I set it up that way to start, just the same way I did before. I take 2 plus h, plug it in for tangent. The difference is there's no algebra or anything I can do with that. You can't distribute a tangent. That doesn't work. There's no such thing as distributing that way. And so what we do is we're now going to plug this into our calculator. Now I've put a box around the part that goes in your calculator. This is just like your worksheet today, right? We take this part, not the limit. That doesn't go into our calculator. I've seen people try to do that, plug that into their graph screen. That really fouls things up. You don't do limit there. You just do this part, except you can't use h's, right? You got to use x's. So I did that over here. I've got my function in here. I've got my table. Now, I did notice one problem here. These don't quite meet. You have to have 3 decimal places. This is 775. This is 773. Well, what do you think it is? I agree. But on the quiz, this table would not be good enough. I know that's getting picky, but I'm going to be picky. You've got to be accurate to 3 decimal places, and I want to see in your table those 3 decimal places. So you better go to your menu, to your table settings. Number 5, you better put in another 0. So I'm going to start at 0, and I'm going to go, instead of 3 zeros, I'm going to go 4 zeros. And then arrow up, and now I can see I got my 5.774. So so that was 77, let's see, I've got 77465. So right here, when I copy down my table, 5.77465, and then here would be 5.774. I don't know what those numbers were. Here it was undefined, and then here it was 5.774, whatever those numbers were, and you copy those down. That's what I want to see. So when it says answer using a calculator table, I want the answer, and I want the table. Yes?
So why do you go to 0 on the table? Why don't you go to 2?
Oh, good question. Because you go to this right here.
So it doesn't matter what you're finding.
That's right. It doesn't matter what f prime of 2 is. And again, that's a good time to review what this limit represents. This limit represents derivative, which means slope at one point. And the way it's one point is the 2 points, 2 plus h and 2, are getting closer together because h is going to 0.
So we only go to somewhere else if it's h is approaching.
That's right. And if it's a derivative problem, you would never do that. You would never go to another. Now, here I'll give you this little hint for tomorrow or about the quiz. The only calculator table one I would have you do, the only calculator limit one I'd have you do is one that's inside of a derivative problem. So they're all going to have that, right? Any other ones I give you, any other limit problems, which we're going to do right now, that go to something else as x approaches 3 or x approaches 4, those are going to be no calculator algebra type ones, okay? That's why the table goes to 0. Doesn't matter what this number is. That 2 is this number in here, not this down here. Yes, Jacob. Oh, Allie, go ahead. All decimal answers, and derivatives, limit, I don't care what we're doing. Any decimal answer has to be accurate to 3 decimal places. Now, that means it can be rounded or truncated, doesn't matter. Okay, but it has to be accurate to 3. If you want to give more than 3, you can. You can give 4 or 5, that's fine. Here's what the graders say. It has to be accurate in the 3rd decimal place. So if they have a decimal, they're going to look and make sure it's accurate in that place. If you have more after that, they don't care. Jacob.
For my chart, I'm getting like 100.
Okay, the only thing I wondered is if you have graphs that I right there. Oh, you're in parametric mode. Oh, okay, all right. So let's do this. Here's what I would do. I would go into if anybody else is getting some other weird table values, because here's what's happening with Jacobs. He's still got his line and ranger things in there, so let's go in. Probably a good idea to go turn off or delete those line and ranger ones. We're going to come back to them later on. But, all right, here's what I want you to do right now. So let's do a couple of just practice limit ones. These don't have anything to do with derivatives. This is one I had up here a minute ago, and somebody said something about bow tie, so let's do it. So so this would be on the no calculator part of the quiz tomorrow. Just some plain old limit problems. Let's do another one here. We've already practiced one like this, but I did all the work. You guys didn't do anything, so this time you guys do the work. Okay? A couple of limit problems. Well, it's no calculator. So, yeah, I would think. Yeah, you know what I mean. Yeah. Go ahead and just do both of them. All right, I'm going to put it up here. Don't look. No, we're still finishing. So on the bow tie one, 3 times 1 is 3. That's where that comes from. X times 1 is X. That's where that comes from. The common denominator would be 3X. Or if you just want to multiply top and bottom, same thing. And then remember what I've talked about here. When you have this X minus 3 in the bottom, it's like you invert and multiply. So bring that up as a 1 over X minus 3, right? Now it looks like it could almost cancel with this 3 minus X. We've seen that several times now. we can factor out a negative, and then that turns that into x minus 3. So now, oh, whoops. And so now those can cancel right there. So we end up with that. And then, like Ryan was asking earlier, we can now let x get close to 3. So now we can let x be a 3. And so we can plug a 3 in, and we get negative 1/9. Okay, so that's a common denominator kind of a limit. And then the conjugate, this is very much like the one we did on that practice sample exam. FOIL the bottom, root x times root x is x, root 2 times root 2 is 2, x minus 2, and then leave the top alone, and then those just cancel. Now you can plug your 2 in for x. Root 2 plus root 2 is 2 root 2. Okay, so that would be a good, you want to practice those, go back and look at that algebra worksheet, the algebra limits worksheet that we did. Okay, go back and try to redo some of those as practice, wouldn't be a bad idea. So that's something that we want to be able to do. All right, here's the next thing. And I'll put these notes up on the website too on the assignment, on the page on my website where I put the assignments. I'll put today's notes, which, so where we went through some of these problems. So here's f of x. Okay, so now we've talked about our limits, and we've talked about the definition of the derivative problems, and we've talked about calculator and no calculator, and what that looks like. And now we've got the shortcut, right? The power rule that we learned. And so here's what I want you to do on this one. F of x equals that. You tell me what f prime of x is. It doesn't say anything about definition of derivative, so that's not involved. This is using your power rule. Okay, I'm going to put it up here. Look if you want. Now, I did a pretty tricky one here. I mean, there may be 2 or 3 of these on the quiz. They may not all have this many kind of tricky ones in there. But if you can do these 3, you can do just about any power rule. Questions about those? Don't be shy. Right? We got to write them as power first. So this has to be x to the negative 2. When you bring the negative 2 down with that negative, it turns to a positive, and you have to drop the power by 1. That's why it goes to negative 3. This is x to the 2/3. When you bring the 2/3 down in front, yes, you may have to go off to the side and do a little algebra or a little arithmetic. And fractions, when you multiply straight across. So 2 times 3 would be 6. 6 over 3 is 2, or you can cancel the 3. And then you drop that by 1, so 2/3 take away 3/3 would be negative 1/3. Now, I would suggest just leaving them like that. You do not need to put this back down on the bottom. You do not need to turn that into cube root down on the bottom. Okay, you need to understand that that's what would happen, but you don't have to do that. Okay, you can leave it just like that. All right. All right, what else do we need to be able to do? Well, if we go back to, my goodness. What was that up there? I don't know what that was. That was my, oh, that's my algebra quiz. All right.
That's our quiz.
Okay, now, yeah, can we do that? All right, so we've talked about this. We just did some examples of that. We've done a bunch of that, and now we get to the chart stuff. So now we get to today's homework, number 52 and number 54, and let's talk about those, and then let's see what we may have time for a quick practice one. I can at least assign you another quick practice one. Number 20 is very much the same way. Now, number 20, I'll just make the comment on number 20. We already have done number 19. We've already done number 21 on that section. That was 2.4. Number 20 is exactly the same sort of thing. Where's a function increasing? Where's it decreasing? Where's the local max? Where's the local min? It's a number line situation. You do the derivative with your shortcut, set it equal to 0, that kind of thing. That's what we really want to get out of all of this that we've learned, is to be able to do these kind of problems. That's the real main goal that we will use more going forward. Okay, local max min. Now, 54 is a little bit of an offshoot of that. So let's go ahead and do that one first. 54 gives you this function x of t equals 3t to the 5th minus, help me out, 25t to the 3rd plus 60t. Now, this is the first one of these you've run into, but it will not be the last by far. A particle is moving on the x-axis. What we have is this something. It's just a way to show motion. And the reason we do it on the x-axis is so we have a numbered place for the thing to be. So think of it like the Bismarck card problem. Bismarck is 0. East of Bismarck is positive. West is negative. Now, you physics people, what did we say if you're moving to the right or to the east? What's positive? The velocity is positive. Now, it doesn't matter where you are. Even if I'm over here on the negative side and I'm moving to the right, the velocity is positive. If I'm moving to the left, velocity is negative. Now, from a calculus perspective, whether you're in physics or not, here's what you want to think about. You want to think about, in our chart, we have f prime, f double prime. In this function, the function is actually called x, so that's going to be x prime, and x double prime. And in physics language, that's position, velocity, and acceleration. Velocity is the derivative. So when the velocity is negative, the position is decreasing. Think about it. When I'm moving to the left, if I'm on the x-axis, now, so instead of pretending Bismarck is here and this is east and west, let's just pretend 0 is here. There's a big x-axis on the floor. 0 is here. I'm over here at the positive. My position is 5. Now it's 4. Now it's 3. Now it's 2. My position is what? Decreasing. Now I'm over here. I'm at -1. Then I'm at -2, -3. Still decreasing. Negative getting more negative. Positive getting less positive. But it's decreasing. But this is right off the chart. So positive is, position is decreasing when the velocity is negative, which means x prime is negative. So this is what the number line tells you. So we have this particle just moving back and forth on the x-axis like so. So when is it moving to the left? You have to think, well, that means when its velocity is negative, its velocity is the derivative. So we need to do the derivative of x prime of t, or the derivative of x of t, which is x prime. Kind of interesting to think of x as the output variable now, but it is. T is the input. X is the output. So this would be 15t to the 4th minus 75t squared plus 60, and we got to set that equal to 0. So as I was walking around, a lot of you did not have nearly enough stuff on your paper for this one, but understand that this is a chart problem. It's the first time we've seen it as velocity. I probably won't ask it that way because it's the first time we're seeing it. I'll just ask it more as a local max min kind of question, like number 20, but we work it the same way. We want to know when this is negative. Why do we set it equal to 0? Because that'll let us draw a number line, and a number line, if we find out when that value, that function is 0, then we can check in between to see when it's positive, see when it's negative. So anytime we want to know if a function's positive or negative, we do a number line. We first see where it's 0. So we want to solve this. Now this would be a no calculator problem. You would be expected to be able to do this without a calculator. You'd be expected to know that you can take a 15 out of all those numbers. That would be the trickiest part of that probably. This is also a factoring thing you haven't done maybe for a little while, but you can do this as a t squared and t squared. That would be -4 and -1. Let me erase some of my stuff here. So I have some room. Now we would factor each of those into t plus 1, t minus, oh, that'd be 2, t plus 2, t minus 2, t plus 1, t minus 1. Probably wouldn't need to, but I need to understand that I'm going to have 4 answers there. I'm going to have plus or minus 2 and plus or minus 1. Now, it did say, of course, 15 would never be 0. It did say in the problem that t is positive. Time was going to be positive in this problem. There was no negative t value, so we can throw out the -2 and we can throw out the -1. And so it's just going to be 1 and 2 that we put on our number line. Then we pick numbers in between, 0, 1.5, 3. And we plug those where? Into x prime. That's why we label this number line x prime. We want to know when our velocity, when our x prime is positive or negative. Now, I would plug it into this version right here, I think. I think that's the easiest version to plug into when I don't have a calculator. Okay? So if I put 0 into there, 0 minus 4 is negative, 0 minus 1 is negative, 2 negatives, positive times positive. Put a 1.5 into here and square that, it's like 2.25 something, but you know it's less than 4, so that's going to be negative. 1.5 squared is going to be bigger than 1, so that's going to be positive. Positive times negative is negative. Put a 3 in there, that's going to be positive. Put a 3 in there, that's going to be positive. And so there we go. So this particle now on the x-axis is doing what? What's its motion look like? Right, left, right. It's going right to 1, it's stopping, turning around, going back to the left, stops at 2, because that's where its velocity is 0. So to answer the question, when's it going to the left? Between 1 and 2. Between 1 and 2. Okay? Between 1 and 2. That looks very much like number 19, number 20, number 21. I was asking a little different way, this thing with the particle and when's it moving left, but it's still a number line kind of a problem. Chart kind of a problem. All right, let's talk about 52. And then I'll give you a chance to ask some other homework ones if there's some other homework ones I may have forgotten a few of those. Somebody said something about 33 or 34 or 35 or something like that. So we may want to talk about one of those. All right, but let's talk about 52. 52 is x cubed minus 3x squared plus k, is that right? And it wants to know now, this probably is a little beyond what I would expect you to do on this quiz. Okay, but it's a really good problem that shows what we can do with this local max min derivative information. They want to know when will this cubic have 1 intercept, 2x intercepts, or 3x intercepts. So we have to pull together a lot of different information of what we learned. The first thing we have to do, this would be a no calculator. What in the world would you do with a k in a calculator anyway? First of all, what's an x cubed graph look like? 2 humps, starts down here, goes up, and then takes off that way. Because we see there's a positive in front of the first term. So, up, down, back up. And it might not have 2 humps. The 3x squared kind of has something to do with that, but it might. Now, if it was just one of these that just kind of curved and kept going up, then it's only going to have 1 intercept. Okay, but let's assume that it does this. So we think it does that. Now, what's the k do?
Moves it up and down.
Moves it up and down. So, pretty soon you start thinking about this and you start thinking, well, geez, this, if it looks like this, that's only going to have 1 intercept. When would it have 2? If that piece, if we shifted this down just far enough for this point to hit, we have 2. But if we kept moving it down, we'd have 3 until the top one hits. Then we'd have 2 again. And then we keep moving it down, then we have 1 again. So what we've just realized by analyzing the problem that far is that the real keys to this problem are the local max and the local min. So what we need to do is find where the local max and local min are. Well, we know how to do that. What do? We do the derivative and we set it equal to 0 because those are the two places when the slope is 0. So we do derivative is 3x squared minus 6x. What's the derivative of k? K is a constant. Derivative of a 7 is 0. So that's good. That disappeared. We can set that equal to 0. We can factor out a 3x. We get x equals 0 and x equals 2. Now, because I wouldn't have to do a number line here because of what we know about an x cubed, and that's not the point of this problem. If the point asks, where are the local maxes and mins, you'd have to do a number line and give your rationale like we talked about earlier. But in this problem, that's not what we're after. So, oh, my drawing is even good. The local max, and we know since this goes up first and then continues up at the end, we know the max is going to come first, then the min. So the max is at 0, the min's at 2, so my picture even kind of looks not half bad. So what we need to do is find out what?
Move it down.
We need to move it down until this is touching. Now what does that mean? We know that happens when x is 2. So what do I do with that information? When f of 2, okay, yes. When I need to plug a 2 in for x to the original, right? Because I know what'll happen if I plug a 2 into the derivative. What? I'll get 0, right? I mean, because that's where its slope is 0. I need to know the y value on the original function when x is 2. So I need to plug a 2 into the original. So that'd be 8 minus 12, that'd be negative 4 plus k. I need to know when that's going to be 0. Because that will tell me when this point is just touching. Well, that's when k is a 4. Now, I keep moving it down until this point is just touching. So I need to plug a 0 in. So that was f of 2 equals 0, you were telling me, right? Now I need to plug a 0 in and see when that's 0. So I put a 0 in here and I get, oh, just k. Oh, that was easy. Put a 0 in there, I just get k. Well, so when k's a 4, this will just be touching. When k's a 0, this will just be touching. Now let's answer the questions. So the question was, when will it have just one x-intercept? When k is greater than 4 or less than 0. It'll have 2. When will it have 2? When k is 0. Right, that's when there's 2 intercepts. When k is 0 or when k is 4, because that's when it'll just be touching off 2 intercepts. And when will it have 3 intercepts?
Between those two.
When k is between 0 and 4, right? So when k is 4, it will just be touching here. Then we keep moving it down, so k is getting littler. Moving down, now k is a 0. Now this top one will just be touching. There you go. So that's a tricky problem, but it's a good problem. It's the kind of problem we'll get more and more used to doing because it doesn't ask anything that seems like stuff we've been learning, but yet it does. Everything we needed to solve it is stuff we've been learning. So we had to analyze it, figure out the local max and local mins were the keys to it. We had to find where those were. We had to plug some values in, and we had to find. Don't anticipate that being something you'll have to do tomorrow, but there's always that possibility that there's some sort of question that seems a little weird and different, but you do have the information to be able to do it, okay? So, but there'll be plenty of others that are going to be just like the stuff we've been talking about. All right. Well, not a whole lot of time left. I guess the last thing I would say, we talked about chart stuff. I'm trying to think of something we haven't went over today that would be on there, and there's very little. I guess the last thing I would mention would be that, oh yeah, we were going to talk about like 33 or something like that. And that kind of references what I was just about to say. we did learn about this capital F business, right? Where capital F is the antiderivative of little f. And so we might be asked some chart type questions on the no calculator part where you have to do this. And I guess one other comment I would make before I let you ask me about the 33 or in that section would be this problem right here, or let's go back to 54. If this was a calculator problem instead of a no calculator problem, it would look exactly the same. You would still need, now what you could do is when you get to here, you might be able to go to your calculator and tell it to solve this for you to get there. So you might be able to skip a little bit of the algebra in here. So if it's on the calculator part, you do the derivative, write it out, set it equal to 0, but you could let the calculator do the solving. But I still want to see your number line, okay? Plotting your points in, but you can use your calculator to help you plot the points. But really, most of this still has to be on here when you're doing a chart type question like this, even if it's on the calculator. I may put a problem like this on the calculator one just to make the two tests a little more balanced as far as how long they are. But you still have to do this, really a lot of the same work. All right, 33, was there anything there? 34, 35, I can't remember. It said something like G prime equals little g. And it said big G of x was x times sine, e to the x. And it said give 3 different antiderivatives of little g. 3 antiderivatives of little g. Well, this line right here tells you that big G is the antiderivative of little g, right? G is the derivative of big G, which means big G is the antiderivative of little g. So give 3 antiderivatives. Well, that's 1. What's another one? Plus 4. What's another one? Minus 4. Or just plus some constant, right? There are an infinite number of antiderivatives of a function, but they're all the same except for just some different constant tacked onto the end. Okay, that's all that problem was about. And so that, again, kind of goes back to this idea of the big F, little f, and chart kind of questions there. So that's it. I mean, that's a pretty good review right there. So I'll post those notes back up there on the website, but the stuff we just kind of went through, look back at the old algebra limits worksheet, practice your algebra on some of those things. I'm guessing, make sure you know the definition of the derivative. We struggled with that at the beginning of the period a little bit. Writing out the definition of the derivative and then being able to work those out. I don't know. I've done all I can do. My work is done. It's up to you. All right, I will be here early in the morning, so if you got any questions or anything. I really don't, and that's what I was kind of saying earlier. Number 20, we didn't go over that one, but here's one I was going to do. If you want to, and this is just one. Here's a problem I was going to do. It's kind of a chart kind of problem. If you wanted to do this, I was going to give you this one, but we kind of ran out of time. If you've got 2x cubed minus x squared minus 3, find local max, local min. Remember the other term we use sometimes is local extrema. So if the problem said find all local extrema, that means find the local max, find the local mins. There could be more than one. And remember how you have to give that answer. A local max is because f prime switches or changes from positive to negative. So if you work it all out, do your number line, that kind of thing, and that's what you will see for a local max. That is a local max right there. This is your f prime number line, and so but you need to write this out. Okay, give your reason why it's a local max. Same thing, local min. But that'd be a good one to do right there if you just want to practice that. But that was the only other one I was gonna do, but that's very much like what we just did on 54. Okay. Otherwise, I think we did, it was getting kind of late last night when I did this. And when I say late, I mean like 8:45. Late for me, my kind of late. Since I know most of you guys do your homework on Sunday nights late, you know, there was a time years ago where students would, well, of course it was years ago, so they wouldn't text me, I guess, or they texted going on then, but there was, I got a few phone calls on Sunday nights, but I'm not up that late anymore. Mr. Martin probably called me late at night on a Sunday night, probably, except I'm not sure how often he did his homework, so maybe not.
I had to.
Do you have a phone in high school?
I got my first cell phone in that little break period between school and graduation. And I had about a week off. That's when I got my first
Between-
cell phone. Between school being done. and graduation my
Senior's
senior
last
year.
day,
Yeah.
senior last day, and
Yeah, kinda right there.
really,
And then
and you're just
I
talking
don't-
one of these flip phones, right, with the
Yeah.
old T9 and
It slid.
texting, right? The slid. Oh, you had
It
with a
slid.
key.